again, I'm just moving ahead with the workshop. I know some of you might still want to talk about your assignment one. We'll probably do that next week, since again, we want to move this forward as a continuation. The techniques going to be covered today will not be the same. It will basically add to what you have done for assignment one. So it's complementary. So we will go back to assignment one presentation, or maybe discussion, and talk about how we can begin to integrate the methods for the second assignment with the first one, and and look at more comprehensively how we can look at a wall system and address that from a sort of more from a larger conceptual perspective. So let's maybe, let me find my notes, talk about so today the major thing that we want to cover is sub-D modeling. Okay, so those of you who don't have Rhino 7 on your laptop, on your own computer, you need to get on Launchpad. So Launchpad will give you access to Rhino 7. You don't have to buy it, but I will suggest you to just bite the bullet and just get it, because it opens up a whole different modeling possibilities for you. It's definitely worthwhile. And then we also want to cover a little bit the techniques that Alexandra mentioned, like origami, how to do something like that within Rhino. I do also want to get to the point where we will be, even though we will be looking at sub-D services, the point is not necessarily just sub-D service. The idea is how to create services that we can unroll, like turning into a three-dimensional form into something that can be cut as a flat pack and then roll it back up into a three-dimensional form. Okay, so that's the ultimate objective. So whether we're doing it with meshes, NURBS, sub-D services, the process of unrolling services and folding it back up, how to create little devices like tabs, like holes, like annotations, so that when you put the pieces back together, you can figure out how all these pieces can fit back together, and then also ultimately origami surfaces. So it's pretty ambitious today. So let's get started. I want to start by going back to the very, very basics of understanding the differences between different geometry types. So in the notes here, I want to basically lay out the difference between what is a mesh and what is a NURB surface, and what is, let's see, let me create a simple NURBS solid, and what is a sub-D surface ultimately. Okay, so a mesh surface is basically the simplest form of how a geometry is represented. So every shape has a vertex, as a series of vertices and edges and faces. Okay, so if I export this file, okay, so let's say if I export this this shape into, so let's just say into a OBJ file, and let's say box 1 option default. Okay, so let me open that file. Oh, sorry. Okay, so this is the test.obj file. Okay, and this is what you find. Literally, it's a series of texts that describes every single point, every single vertex. V is a vertex, right? And then the X, Y, and Z location. So however many vertices that this object has, right? So it's all under here. And then if you scroll down, some point you to find the vertex normal, Vn, right? Normal means what is pointing, the vector that's pointing outward from each vertex. And then you have a face, F, so that's basically, again, how meshes are defined. Why does it matter? Why do you care? Well, every time you render something from Rhino onto a screen, Rhino actually converts a NURB surface into a mesh form. And so I don't know if you guys ever encountered this, right? Like when you have a curved object, but when your file gets really large, sometimes you see a curved object is showing facets, when you see it on the screen, right? Or sometimes when you do renderings, it happens quite a bit if you actually ever use Maya, because you have to define the setting yourself. But Maya, again, don't always give you the smoothest curve, because when you render an image, it turns a curved surface into a mesh surface before you can actually display onto the screen, right? So it's going through a conversion where it basically tries to tell the computer that you want a certain level of curvature. So it moves from a mathematically defined curve to plotting actual points in space, right? And in this case, it's trying to plot a number of points along the screen, so it's displaying something that's smooth. Okay, so every time you move an object from the digital space to the screen, or to 3D printing, or to laser cutting, you need to turn an object from whatever form it takes, whether it's NURBS, a solid, a sub-D surface, everything goes out to the physical world in mesh forms. Okay, so you need to understand that this is the rawest form of a geometry representation. Everything goes back, everything will ends up as a mesh, whatever it is you begin with. Now, nobody likes to model as a mesh form, because I simply cannot manipulate this geometry. In order for me to manipulate this geometry, I literally have to go in and start, pulling points, like move point to point. In Rhino 7, I can also start to move faces. If I hold Shift and Control at the same time, I can click on an edge and start moving an edge. I can move a face, Shift and Control, move edges. Okay, so because it's the rawest form of geometric representation, I don't have a higher level function to manipulate this as a overall form. I don't have an effective way to sculpt this. There are a lot of software today like ZBrush, Blender, other platform. They'll give you like a paintbrush to basically in large stroke sculpt a mesh surface like this. So people do 3D scanning data, so the data is really, really messy, really, really coarse, but it really describes every nooks and crannies that our face or bodies has. And so people actually just like to work with that really raw, really unstructured form of geometric data, but using again higher function like a brush stroke to paint and to start sculpting objects with it. But Rhino don't have those functions, and again, it is different kind of technology. It's image-based modeling instead of mathematically based modeling. So we want to be able to understand the different processes. NURBS, on the other hand, it's basically, we talked about this quite extensively last time, in terms of the kind of mathematical function that's driving through the shapes. So for example, if I'm pulling vertices around and start to sculpt this, it actually because it's mathematically defined that between these 2 points everything should be smooth and continuous, right? So it's actually allowing me to sculpt in large strokes what this whole shape could be, and it maintains continuity. Okay, so so that's sort of one of the issues that we will begin to encounter when we move into a sub-D modeling process. So what I want to show you guys also is you can see here there are different ways to display the objects because there are different terminologies associated with mesh surfaces versus NURB surfaces. So you can see here, the edges here are pink. So you have such a thing that's called a naked edge when you're creating, mesh surfaces. Okay, so that's a naked edge means the edges are exposed to nothing, right? So in this case, here is another edge, but the edges are actually touching the other surfaces. So these are not naked, so they have slightly different color. But edges can also be welded together. So let's just do something like this. So if I actually pick an edge, and so we can see here, because meshes are, again, points, vertices, edges, and faces, I can actually have a situation where there are two. When you have vertices that, like right now, these four faces share a single vertex, but I can unweld this so that the vertices are split up. And that means that when I click them, they are no longer together. So meshes can have this property, that we will call welded or unwelded surfaces. So sometimes you need to be aware of situations like this when we're modeling with such complexity, because now we have a situation like this where the surfaces are split. That's another interesting properties of meshes, because with NURB surface you can never create something like this, right? There are ways that we can model in meshes that you can never imitate with NURB modeling techniques. So they give you a different formal language. You design differently. You can actually create different forms with the techniques that you cannot do with the other one, right? So from a design perspective, it's interesting, and it's actually also very important for you to understand the differences and apply the technique to get to the form that you want when you need to. Okay, so I want to show you how you can begin to show these different properties. So again, showing edges is one important thing. Showing face orientation is another thing. Okay, so when you model a surface, there's a front face and there's a back face. So right now the front face is the object color, but then all the back faces, whether it's a mesh back face or a NURBS back face, is shown as another color. Now this is important because normally you don't really care about what face the surface is, what is front, what is back. But when you try to unroll, like try to fabricate things, the orientation of surfaces becomes important. So the setting that you want to change here is when you go right click on the screen here, perspective, click display option. And then, so right now I'm only affecting the shaded view. So under shaded, if you scroll down here, back face setting, I can use a single color for all back faces. So that's one of the single color for all back faces. And I can pick what color I want, right? So I can, change it to a slightly less pungent blue. So that's one thing that you want to do. You want to always know what the front face and what the back face is. And then if you click under object and show the meshes, these are the the edge property. So you can show edges of a mesh. Actually, I will show normal edges as just the object color and not change it to a different color, but only naked edges that has been delaminated, right? Edges that are simply overlapping. They belong to different surfaces, but they're just overlapping. So sometimes you think that, oh, it's a good object. So this is what we call a watertight object, right? So and when you have a watertight object, only watertight object can be 3D printed. If you have an object that has, like loose vertices or loose edges, meaning that they have been delaminated by accident one way or the other because you're modeling in such, fancy pace, you forgot, to check. So I always check that, the naked edges should show a different color. So that makes me aware that this is a watertight object. This show no signs of naked edges. This one, there are naked edges everywhere. So I need to be aware that something is wrong with this geometry. This cannot be 3D printed or, like whatever I want to do with it. So this will give me problems down the line, okay? So with that setting, I have a lot of what I need to move forward. So I'm going to delete this and go back to one of the things that we talked about, in terms of moving forward with, why we need yet another way to model, which is sub-D surface. So let me just bring up a screen. So at Catmull, sub-D surface, subdivision surface is also called Catmull-Clark surface. Why do you need to care? Because Ed Catmull is, or right now, he is the president of Disney Animation. He used to be the CEO of Pixar. His thesis, his PhD dissertation is the modeling of a hand. He created this way of modeling to create more organic models. So as I mentioned before, NURB surface emerged out of the 50s and 60s in the car industry. Okay, it was a way for people to understand how to translate people that used to build boats, how to bend wood planks, a spline, right? And creating a mathematical equation to describe that curvature and allow, more consistent, allow machines to recreate those kind of curvature consistently over and over again, okay? So NURB surface came out of the car industry. Now, it also points to a problem. There are a lot of things that, other industry, people in other industries, like the animation industry, cannot do. For example, the modeling of a simple hand. The topology of a hand is so complex that you simply cannot model a hand with NURBS, which is not possible. In fashion industry, you simply cannot model pants with NURBS. It's something as simple as that. So this was literally, his PhD dissertation. So that can't model. Right. So this was his PhD, and after his PhD, his dissertation, he actually founded Pixar not too long after and created a whole system for character animation. So, Toy Story was the first application fully rendered, of his technology. So right now, Rhino 7 just implemented sub-D Catmull-Clark surface into its software platform. In Maya was one of the earliest commercially available modeling platform that you can do sub-D surface. This was early 2000s. So people have been playing around with this for almost 20 years, and again, it just became available with Rhino because Rhino has been a favorite among architects because the level of precision, the level of manufacturing capability, the way it's open source, everyone can tap into the source code of the modeling technology. So, with them opening up to Kendall-Clark surface, it's actually quite a big deal. So one of the things that makes that's different between, why do we need sub-D surface? How is it different between mesh and NURBS? So let's maybe jump back to where we talked about the relationship between, when you're drawing a NURBS curve, the relationship between a cage, again, I'm calling this a cage. It's a common terminology. Most people would recognize it, but different software call this differently. So Maya call this something else. Alias Wavefront call this something else. Sophie Marsh call it something else. So, but cage is something that is kind of universally known. It's about the relationship between this rectilinear form versus this curve form, right? So if I click this curve and press F10, I'm manipulating this object, right? So sub-D surface allow you to, basically switch between something that's rectangular and something that's curved. So in a way, it's the best of both worlds, right? Because you can actually go back to the mesh modeling mentality. You're always just manipulating vertices and edges, but now you can also control, the curvature of a form and actually begin to, create more details. So for example, if I don't want the shape to be so bulbous like this, I can actually always add more points, add more details to the shape to change the curvature, to change the appearance, right? So, this is a kind of method that gets used quite a bit in the car industry. Right? So I have full control over how much curvature that this object or this shape has. I can even remove some points, right? So now imagine this, but in three-dimensional form, right? So that's sort of one of the things that it's very, very different workflow when you're working with the sub-D surface. So I am going to maybe just jump into this a little bit. If you look into the sub-D tools menu, I want to just show you probably 90% of the time you will just rely on this one tool, and it's like right in the middle called single sub-D face. Okay, there are many ways to model in sub-D, and a lot of times of this whole menu set, I would say maybe 2 or 3 of them are actually useful. The rest you almost will never touch. Like you will never do a sub-D loft, you will never do a sub-D sweep to rail, you'll never start building a sub-D cone, right? A sub-D multi-pipe can be useful, but only for specific reasons. So I will start with this single sub-D face. Okay, so let's say you click on that. Now this can be a very intimidating sort of command dialog, right? So let's walk through all of them. Up here, you want the output to be a sub-D surface, not a mesh. Okay. You want it to be interpolated. You don't have to care about what that means for now. It doesn't really mean much at this point. Append. Again, I will do this once again and show you what that means in a little bit. Polygon type. So I'm going to maybe in the note at this, let's see. So, in modeling, same thing, mostly in meshes, you have I think we talked a little bit about this. Okay, so you have, let's see, meshes that forms a bunch of polygons at the end, right? So in the case of a sphere, you have polygons here that are quads. Quads means, you know, four-sided polygons. And so you have mostly quads, and then at the polar points, polar region, you have, you know, triangles, tris, okay? So most commonly found polygon types in meshes are triangles and quads. Most meshes don't like anything that has more than 5 edges. So when you have polygons that have more than 5 edges, it's commonly just called an n-gon. Okay, so n-gon, it means it doesn't matter whether it's 5 edges, 6 edges, 7 edges, 8 edges. All of those, to me, it's the same. It's just an n-gon. It's just anything that's more than 4, and they're all shit geometries. I don't like it, right? So it literally, you know, n-gon means that you know, I don't give a damn about what that is, how many edges anymore, because you know, to me, it means, you know, there's no difference. So sub-D surface can handle n-gon, but not beautifully. So you don't want to be, you know, doing things with n-gon. So you want to click on it. You don't want it to be triangles. You want it to be quads. Okay, quads has a huge advantage because quads, like in a NURB surface, quads means that you have 2 axes that you can deal with. You can have an x-axis and a y-axis. Okay, so having that means a huge makes a huge difference. You know, so let's just go with quads always. From edge, yes. Okay, so I will show the difference. So with the rest of the parameters, you can probably forget it. Now we can start, you know, building shapes. Literally, you are just drawing. I'm from edge. Oh, not from edge first. So literally, you're building quads, right? So you just give it 4 points, and now it's a quad. So now you just build the first one. Now what? I want to build, continue to build, you know, the shape. So you want to, oops. Okay, so let's close it first. You want to click on single sub-D face again. So let's do it one more time, okay? Output sub-D, not interpolated, polygon type quad, from edge, no, in place, no, blah, 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 okay. Okay, now finish by right click again. Click on this one more time, single sub-D face, and now from edge, yes. Okay, we're gonna do one more time. Highlight the shape that you want to add to. Okay, click on this one more time. So you don't see append anymore. So now you're appending to the shape that you just picked, and you want to continue building from edges. Okay, so what that means is when your mouse moves close to a certain edge, so now that means that you're building on that edge. So when you click, okay, you're adding shapes to it. Okay, so now I'm clicking. Okay, so that means that I just picked the edge. So now I need to add 2 more points because the original edge already has 2 points. Okay. Okay, so right click to finish. Now, if I press tab, it shows me, you know, this is the actual shape in polygon form that I've been building. Okay, I can still move things around, but if I press tab again, it shows me the smooth form. I can come in here again under the sub-D menu, right? I can show control polygon, object polygon. So now I see both the relationship between the rectangular shape and the curved shape. So I can come back and begin to manipulate the object, right? So, for example, go back to the situation where I simply want to build something complex like, like pants, right? Something that comes out of one body but have two fingers. Extremely difficult, if not impossible to do with NURB surfaces, but it's just kind of trivial with sub-D surface. Okay. So I want to open this up. So now you have a flat form. What do you want? What can you do to begin to give it some three-dimensionality? And so, for example, I can come in here and insert an edge. So let's say, so insert edge loop, right? So left click, I click on an edge that I want to basically replicate. I click on the edge and then move my mouse to slide the edge back and forth to determine where I want that to be, right? So now I have a shape like this. I hold Shift and Control together, double click on this edge to select the whole thing, right? Double click this whole thing, and now drag this up, right? I can show the control point. I can now also come back and, let's say match this somewhere around there. Is everyone following? Am I moving too fast or moving too slow? Just let me know, okay? Right. So I can do something like this very, very quickly, right? Now, if I'm rendering, and this is, let's say, a roof, I want to, create an offset and give it thickness. So it's as simple as just coming here and clicking offset sub D, give it a distance, say it's a solid, don't offset both sides, just offset one side. Oh, it's way too thin. So let's do it one more time. Distance would be, let's say 1. Okay. So, it's a perfectly offset object. And it's now ready to render and 3D print it. So you can just, if you want to 3D print this, what I would do is make a copy, click here, quad remesh. So you're turning this object from a sub-D surface to a mesh surface. Okay, and I want the target polygon count to be around 2,000, not too many, not too crazy, right? So now that's a mesh. It's ready for 3D printing. Okay. 3D printing or milling or any sort of digital fabrication process, it's ready to go. If I'm rendering, you can pretty much just render this. If you're rendering within Rhino, if you want to bring this object out to some other rendering platform, then you need to export it as most likely a mesh surface or as a NURB surface. I don't want to get too much into that. You can just do, well, maybe just go through this. Over here, convert objects to NURBs. So click on it, right click again. So now it's a NURBs object, right? So it's practically just one click. So now this object can go anywhere. So if you want to just extract lines and bring it into Illustrator for, for illustration, for annotation, that's what you will bring, right? You bring a NURBS object into, extract the outline, do the make 2D lines, right? So you can get a beautiful line drawing out of that. So we still have two sub-D surfaces. So now you have a mesh object, a NURBS object, and a sub-D object here. Again, a mesh object is when you want to bring it to rendering, milling, do something with it, because you can no longer touch this anymore. Like that means that if you want to continue to adjust your design, this model is garbage. You will never touch this again as as part of your design process. This is really just sort of outgoing, the last step when you bring this object out to fabrication, to rendering, all kinds of stuff. Same thing here. You can come back and start to model and do other things with this. And I'll walk you through some of the workflow that we will be working with today in terms of folding and unrolling. That's the object that we will work with, but it doesn't give you a lot of flexibility to continue, to modify your design. So again, consider these as sort of one of the last steps in the whole workflow. Okay. So as you can see, again, I can explode this and remove different surfaces. So it's just a simple single, NURBS curve. Okay. So I will maybe walk you through another tutorial next time in terms of ways that you can do pretty complex modeling technique for like modular based wall systems. Like we looked at Irwin Hauer walls earlier in the sort of course presentation. So I will show you some techniques of doing those kind of very geometric wall system, modular based wall system, how you can model that. But we want to move through to the sort of fabrication techniques today first. So I am going to walk through how we can then make this unrollable, that you can cut on the zoom and then come back and fold it back into a piece that look like exactly like this. But before that, can I just make sure that you guys are all good so far? No questions? Okay. Oh, by the way, John, have you guys used have you guys modeled in sub-D so far? Have you been using it?
Just a little bit, yeah.
Okay.
Not super widespread.
Okay. So I want to walk you through this technique, feature that it's in Rhino, and it's pretty robust. You can take shapes and unroll it, unfold it, right? So for example, if I just come here, create a box, right? I can just start typing, unroll surface. Okay, right click again, and it will show me how this piece can be unfolded into individual faces. So when I cut this out, I can stitch it back together to form this shape, right? So let me do it one more time and walk through the parameters. Unroll surfaces. So when I do this, now they're all in different pieces because it's been exploded, right? So if I do it one more time and then say, don't explode this, right? So it will try to keep all the edges intact and stitched together, right? So here, instead of having all individual faces, you have sort of conjoining edges and then the sort of naked edges. So this is the cut line, and then the rest are the fold lines, right? So you can see it a little bit better here. Okay, so for typically, for simple shapes like a box, this process is pretty easy. Now, let's see what happens when we try to unroll a cylinder. Do not explode, right? So it's giving me this, right? So assuming that, this long piece is the thing that we know that we have to fold, right? We have to kind of roll it along the curvature of these two circles, will come back as a shape like this. So that's good because we know that Rhino understand curved surfaces. And this is an example of having to unroll a surface that's been curved. So it knows how to handle that type of surfaces. Okay. So now let's look at a sphere. Right. So again, unroll. Now it's giving me a problem, right? Unrolling doubly curved surfaces will produce inaccurate results. So now we are encountering this property called, what a rule surface is and what singly curved or doubly curved surfaces means. Doubly curved surfaces simply means that a surface that is curved in both this direction and this direction. Okay. So if I, let's say, make a loft, right? Right. So you can see this surface is curving in both the U and the V direction. So that means that it's a doubly curved surface and I cannot unroll something like that. Okay. That's why but you can also say, wait a minute, TWA terminal, I've seen constructions. This is a doubly curved surface, right? It's made out of concrete. So obviously there's a way to construct these surfaces. Not that you can simply unroll, the whole freaking airport terminal into a flat surface, but I want to go through how something like this is constructed, and it's using a property called a rule surface. Okay, so come back to the idea that surfaces that's only curved in one direction is fine. Only curving in two directions is not fine. So how do we deal with something like this? Turn a doubly curved surface into a singly curved surface. So the trick is called a rule surface. Rule surface means that I can have a curve that goes from one direction, for example, like this. Yeah, my workspace is getting a bit too messy in here. Okay, so I have a surface that's been lofted. So the surface is curved, but as I cut sections through it, I always get a straight line. That means that, even though this surface seems, it has curvature, but it's actually a singly curved surface, right? Surfaces like this can easily be unrolled, right? Again, if I contour this from here to here, oh crap, it's way too dense. Okay. One more time, contour, correction. Right. So you can see. So what this means is similar to the boat construction, right? all you're doing is actually overlaying straight wood planks along the surface, but by actually moving, according to a certain axis, you can actually recreate curved surfaces. So this is called a rule surface. I don't know if you guys are familiar with Preston Scott Cohen. Let's see. So the Tel Aviv Museum, actually, I worked on this when I was in grad school with him. Me and Andy Saunders, two of us created this whole competition package together. So the whole, he loves projective geometry, and almost all his projects make use of this idea of a rule surface. So this is the light fall, as he used to call it. It's this sort of atrium, skylight spaces. So every single surface is curved ultimately, but they are singly curved. So it's very, very easy to manufacture. Like, what that means is, to recreate that curvature, you simply use straight studs and drywall, and use this patch stucco to make the seams a little bit smooth, but extremely, extremely easy to construct. It's the same construction method that the TWA terminal and almost most other contemporary buildings are made. So let's turn this into a doubly curved surface, and we can actually turn this into a singular curved surface. So we don't always have to just construct a curve that way too. So what you want to do is rebuild this. So just type REB to rebuild. And you can see here the point count between the U and V, and then the degree, of the U and V. I hope you guys kind of understand what those means. Point count is just how many lines, how many isocurve that exist within the U and V direction. So if you don't know which one is U, which one is V, you can see the arrows in here. So typically the red arrow is U direction, V is the, red is X, Y is, so you can see here, Y is green. So the equivalent of that is red is U, and green is V. So let's say I want to break down the strips this way along the U. So, let's say there's 15 points and I want to do 5, just visually I can see. So, right. So five counts mean 5 points, 1, 2, 3, 4, 5. 5 points along the V direction give me 4 segments, okay, 4 strips. So now we're talking about how many strips, how many facets do we need to approximate that curvature that I would be satisfied with. The more there is, the closer it approximates the curve, the more work you have to do. So let's just start with 6. And then over here, I want the U to be degree 3, because I want, this side to still be a curved and smooth surface, except that the, in this direction, I want each segment to be, straight lines. So when I take a contour, a section cut of it, it's straight, right? So now this gives me a series of degree 1 or singly curved surfaces. Okay, now can I unroll this? Right. So what that means is I can already, depends on, I'm going to make a copy. I'm going to rebuild again. Right. Depends on how, I want to handle, how many segments that I want. Right. I can build one that has 8 segments and then unroll. Right. So this gives me, so what that means is if I go and cut this surface out on the Zune and then begin to stitch these edges back together, I will get this shape. I will get a very close approximation of this original shape. Okay. If you don't like the way it looks because, you know, like it has too many, or the segments are too big, well, we built this with a higher level, you know, 12, right? So you have full control over this process. Okay. So that's actually one of the tricks that, again, you know, for some reason, not many people are aware of. So if you hide the ISO curve, right? So you can see it's really, you know, a single surface, you know, that's been creased at, you know, at certain points to create a kind of hard edge that allows you to unfold. I mean, yeah, unrolled. So I want to bring up a workflow. So if you open up Grasshopper, you see a file in our shared folder. Flatcut tabs. So what that is showing, so it's, let's say okay, I'm happy with this. I want to go with this shape and I'm gonna, you know, cut this on the Zune and stitch it back together. The issue with this right now is when you try to glue these edges back together, it's an extremely thin edge. You know, you'll have a really hard time merging them perfectly and then have a strong, you know, edge connection, right? Like you have basically a butt joint. You know, a butt joint is not a strong bonding surface, right? So what you want to do is to create tabs. So this file gets, you know, help you create tabs very, very easily. So what you need to provide is to go curve from objects, duplicate border. So now, you know, I have a border object. And if I feed this border object into this, oh wait, I need to select multiple curves. So one more time, duplicate border. So now multiple curves, so set multiple curves. So now it's created a bunch of tabs, except that it's kind of way too small for me to see. So I can see here offset distance, right? So I can actually make it offset a bit more. I can increase the number of tabs or decrease the number of tabs over here, right? So then what that means is when I go and fabricate this, I can take these cut lines. Okay, so what I have essentially, the green ones are the cut lines. I also give you the lines or fold lines, so you can actually get the Zune to slightly score these lines in between. So, you know, it gives you a fold line sort of guide curve. So together with these two sets of curve, you know, it makes reconstituting back from a flat pack surface to a three-dimensional surface very, very easy. Okay. So this is a really good workflow if you want to just play around with it. You know, you want to freehand model something, and at the end of the day, you want to just use a, you know, again, use manually unroll this and use Grasshopper to give you a series of you know, Flatcut tabs. So this file is not that intelligent, you know. So sometimes the tabs might go inward. So you know, you just need to sort of visually evaluate and figure out which side you want to offset the tabs into. Okay. I also have a different file that says unroll with tabs. Okay. So this one tries to be a little bit smarter. So you only need to feed it this object. Okay. Now, with Grasshopper, this here, the brep, the boundary representation object, it's now recognizing the shape, but it's not unrolling. Okay, so I want to show you another process to make that work. So Grasshopper doesn't immediately recognize that these creases should be treated differently. The Rhino command is able to recognize as special. It's smart enough to do that. Grasshopper, however, is not. So you need to do this one extra step. Let me just make another copy. Go to surface edit, divide surface on creases. Okay. And then right click. So now once you do that, you see here, Grasshopper recognizes that shape, unroll it for you. And you can then get the tabs that way. So you can see it's a little funky here because it's trying to give you, I don't know, not 21, but some amount of tabs, both for the long edge and the short edge. So what you want to do is to bake tabs for the long edge, and then delete the tabs for the short edge, and then rebake the tabs for the short edge with fewer amount. So let's say for the short end, you might not even want tabs for the short end because again it's like there's no tabs here. So, but that part will be a manual process. Okay, it's much easier, right, than to try to come up with another extra 20 nodes to try to figure out how to understand the short ends and versus the long end, so that it will give you a different amount of tabs. It's much easier to just do it visually. Okay, so same idea. I can come to this this object that we just modeled from a sub D surface, convert it into a NURBS object. And now we can pretty much do something very, very similar, right? Turn this into an object that has these sort of folding creases and then unroll it, right? So let's just go through the steps, rebuild. So let's see. So you see now the creases is going the other way. So I want to rebuild again. So let's just do 6, 15, 1, 3. So you can see the surface orientation is different. So I'm going to just do it the other way. 3. This is the tricky part, right? Because now I have a situation where I need to match this surface with these two. Okay, we can come, let's see how it looks. Figure out a way to handle it. What I'm showing you here, it's called design engineering. It's actually a thing. There are people, structural engineers mostly, and then there are a lot of computational designers whose specialized job is to take the model that someone just freehand draw, created, wacky, crazy services. They don't know how to build it, and then these guys spend basically their career trying to figure out how to turn an object and turn it into something that's buildable, right? So something like this, right? Again, traditionally very, very hard for a NURBS model to handle. You know, it's not easy, right? So what that means is I want to be able to split this surface right in the middle. And so this side can match this surface and this side can match that surface. It will take me probably a bit too much time. I will record this as a video and show you how to do it, because otherwise we'll completely run out of time. But we'll show you, it's not a foolproof process. You have to sort of be able to break down shapes and you know, from very complex form to something that's much simpler, okay? But what it can look like, right, is simply coming in here, grabbing that point, pointing it over here, creating a surface that you can use to split this. And so now you can rebuild those two parts separately to match each side of the surface, right? So the process will, you know, simply be something along those lines. Right, so you can see now I have this, the faceted edges on this side and faceted edges on this side. Yeah, I can actually simply even just go in and start pulling edges and try to, you know, bring them and match them back together. Or I can use the functional match curve or match surfaces to, you know, to make the two surfaces match back together. Again, it's a bit more involved process. So I'm gonna just, you know, try to record this on the video instead of directly walking you guys through it right now. Okay, so let's just once again do another example of something that you can draw freehand, right? So let's say, let me walk through this one more time, delete everything. If you are in our case, right, like we're trying to use this as a way to build the structure of a wall. Assignment 1 is about the skin. It's about perforation. It's about, you know, creating a large surface area that can be, you know, perforated to modulate light, modulate sound, modulate whatever, right? What this exercise is that it's because the thin skin doesn't have any structural strength or properties. So it would just, you know, flop around. So now what we want to do is in the second part of this exercise is continue to use the folding as a technique to create structural members for the skin that can, you know, so that the skin can attach to the structural component to give it rigidity. So, you know, like I'm not expecting you to be, you know, like doing crazy complex doubly curved surface or whatever, you know, like it's not necessary. You know, if we go back to the assignment 1 parameter, you know, start with the module. You know, the module is 48 by 36 inches. Again, you know, some of you have changed the dimension, you know, so Emily, you're working with a wall that's more like, you know, 6 feet by 9 feet tall or something, right? So imagine then the module will be, you know, 6 feet, half of it will be like, do you want to work with 3-foot modules or 2-foot modules? So you have 3, you know, on the bottom, and then the height, you know, so you have to figure out what your single module dimension size is. But, you know, for us, the idea is I'm giving you the technique and you can kind of decide that on your own. It doesn't really have, it doesn't really make a difference for us at this point, what exact dimension you go with, right? So for example, I want to create something, again, let's say, how about something like this? So one of our images has a sort of forest themed image. And what we can do is perhaps create some sort of geometric pattern that approximate that kind of organization. Okay, so one of the functions that you can do with, so let's say, again, for example, let's say this is the pattern that I want to work with. And one of the functions that you can do with sub-D surface is a multi-pipe. So let's just do a multi-pipe and see what it does. Multi-pipe radius, set to 1.2. Caps off. Ooh, okay. Let's go with a different radius. Okay. So let's say it gives me structural members, right? So let's say, you know, for example, these are the structural studs that I can work with. I'm not doing this to say I want to do curved surface, right? But I'm saying actually this gives me a very quick way to create these kind of joints. Because you know what, for me, even if this is sort of rectilinear tubes at the end, and I can actually come back and unfold or unroll this very, very easily, very, very quick. You know, I don't have to do, you know, all this crazy, you know, curved surface. Like I don't have to come back and, you know, rebuild each segment and then, you know, unroll and unfold back. This is structure, right? So I can simply come in here and say, can I unroll this at this point? It's not giving me the unrolling. It's not unrolling for me. So I'm going to come back and start to simplify this. You know, all right. I have to turn this into a NURB surface. Yes, no. Set the option. So what I'm trying to do is when I turn this into a NURB surface, I don't want to get the curve, the smooth option. I want to get the cage. I want, you know, this cage to be exported. It's there. I forgot exactly. From control poly, okay. So now I'm basically turning the control polygon into a mesh. It doesn't give me straight NURB surface. So what I need to do is to then mesh to NURBs. Okay. So now, basically from something that I sketched very, very quickly, a series of structural members, and then use the multi-pipe tool in sub-D surface. I created something like this, and now I extracted the, so let me move this accordingly. I extracted the control cage into a mesh, because that's, what Rhino does. Only give me extract mesh from control polygon, right, into a mesh. And then using the function mesh to NURBS, I created back the sort of BREP object from that. And then, doing that makes this unrollable. But now you see it's a big jumbled mess because, again, it has to do with, being able to simplify objects. So let's say doing things one by one, right? So let's just look at unrolling this one part, right? And then a second part here, join them back together. So for example, if these two parts. So now I have this part and this part, they both look good individually, right? So let's say one more time. Move everything out of the way. So this part is this, and it looks good. Seems like you can easily unroll it and stitch it back together. This part, again, looks good. So, it's really just the process of coming back, joining these individual faces back together into an object, and then, figuring out what part belongs to what, and then go through the unroll process. Okay. So again, it's not simply one click and, I hope it's that easy, but as the object gets more complex, you have to figure out, better ways to sort of overcome the complexity and find a process that can give us the result that we want. Okay, so this one seems like, we have an instance of a singly curved surface, a rule surface, right? We know that Rhino can handle rule surface, so it shouldn't be a problem. Okay. So this one you can see here, because the way it is folded together, it's giving us, overlapping edges. You don't want that. So so when you say joined, unrolled, it's false. When you bake it, whoa, actually, I don't want this tabs right now. Wow, just take a look. So when joined is false, when you bake it, they are individual surfaces, right? So what that means that is when you bake this curve, even though they look like they overlap, they're actually not overlapping. Right? So you can see here, these curves. Okay, one more time. Okay. Goodness. One closed curve. Okay, I'll give you a file so you can just feed um, the shape into Rhino and get the tabs, to make that process a little easier. So let me just maybe do this right here really quick. Yeah. So now this file, you can basically unroll the shape. If they're overlapping, giving you a problem, move them out, explode it, and then here you can extract the curve directly on the shape. Okay. Again, I'm not gonna lie, it's not. It can be laborious, right? So don't go too crazy with, like you don't want to be gluing 10,000 surfaces back together. Not even 1,000, hundreds maybe, but like this level of complexity is probably a bit overkill, right? But what I want to show you is this is somewhat of the direction that that I want you guys to go with, right? We're doing skins and bones. First exercise is skins. Second exercise is bones. How do you create some structural member, create rigidity, create volume with folded surfaces? Everything that can be flat pack, assemble on site, easy to transport, super lightweight, right? Because what the implication is, we have a cavity, we have a void here. It's flat pack, glue back together, and the inside cavity can be filled with spray foam, like expanding foam. It's not entirely sustainable, but foam will give it rigidity. There are actually mycelium alternative that we can grow mushroom inside these tubes, because mushroom can actually basically they turn into foam, as a sort of foam replacement. So there are sustainable ways to do it. It's just, if we're prototyping, go to Home Depot, buy a can of spray foam and fill it. It makes it super rigid, right? So yeah, we are aiming for a full scale prototype. So don't have to go too crazy. So that's kind of the overall objective for this part of the exercise. I know some of you want to explore origami technique, as Alexandra mentioned. So the last file I want to show you is that, origami. K2. So I have a file. Let's see. It goes along with that. I'm throwing a lot at you guys. So yeah, so I want to maybe spend some time to just like, have you guys play with this a little bit so you guys have time, to ask questions. So Grasshopper has a plugin called Kangaroo. So Kangaroo 2 is the plugin that we will need for this file to work. I checked, it comes with Grasshopper, I believe, because it exists in all the Grasshopper versions on Launchpad. So if you're using Launchpad, I checked, you should have it. If for some reason you don't have it, just download it. It's free. Okay. So I want to walk through this. The basic file setup is it's this. Okay. I know it's kind of confusing. Like, what is this? This whole part that is inside this purple rectangle, you almost don't have to know what they're doing. It's basically sorting lines and trying to figure out, what lines belong to where and how to, like, that's the complicated stuff that, yeah, you really don't need to bother yourself with. The only thing that you need to know is you need to feed this file three things. One is a mesh of again, the whole idea, let's see. Right, the idea is to create folded shape that is based on a certain pattern. Okay, so for example, something like this, right? So you're creating a modular shape, and when it's folded consistently, right, it turns into a three-dimensional shape. So what you need to provide with Rhino is a basic flat pattern of a mesh that carries that shape, and then valley fold lines. You have to basically tell Rhino that which lines should be, folded, the valley lines, right? They're folded downward, and which lines are, the mountain lines folded upwards. So 3 sets of information, and you will be able to simulate the folding pattern. So I have a file here. So I can sort of show you what that might look like when you run this file. So this file that I sent you, maybe I'll just use that example, has a mesh, right? The mesh basically has the geometric pattern, right? And then has a group of line on a different layer called mountain fold lines and valley fold lines. So you can right click and select the objects. Right? So just 3 sets of lines, and then the valley fold lines right here. So they should all overlapping one another, and they should be mapped. So this is so I'm going to hide these for now. Okay, so we have the mesh object, the valley fault lines and then the mountain fault lines, okay? So when I toggle this Boolean toggle, click to true, and start to click on this reset first, right? And start to move this over here. So you can see it's folding, but you can't really see it too well because it's kind of being obscured by the other object, okay? So it's basically a Kangaroo has a simulation system. It's telling the edges to remain, to not stretch. You know, so it's a sort of rigid body. It's a physics system, right? It's trying to simulate objects colliding with one another, or like springs that edges that can bounce back and forth. You can simulate all kinds of stuff. So in this case, it's trying to simulate a behavior where there are a bunch of hinges that you can change the angle and the strength of the hinge. But if you make the hinge strength too high, it will start to rotate and do all kinds of stuff. So all these slider bars are basically trying to control the behavior of this simulation system, so that it gives us the result where we end up having a shape that we can bake, right? And it's a folded shape. It's not perfect. You can see it's still simulating, still slowly drifting away, still rotating. So we want to just move it outside and, maybe just rotate it back. Okay, so that's how you use the file. Okay, simply come in here, turn on the Boolean toggle. So if I show this again, reset, we'll make it flat and then start simulating again. All right, so if I change any parameters, click reset again. Okay, and then this one will begin to fold. Like this is the controlling the folding angle. Okay. Okay, so that's how you use the file. So when you're done with it, click the Boolean toggle again. It basically freezes the shape. You can bake it. You can, let's see. Yeah. So, but again, it basically gives you a visual simulation of what the folded surface will be like. But that's not what you will bring to the Zune, right? The Zune machine, what you will bring is the original file where you have these lines, right? This is the valley fault lines and the mountain fault lines, right? And then you want to extract the outline of this shape. That's the cut line. So the valley fault line and the mountain fault line. So this file will do a double-sided cut, or double-sided score, not cut, right? So you want to score the valley line on one side of the surface and the mountain lines on the other side of the surface. So you want to create registration dots, accordingly. But theoretically, if everything is going perfectly, you will get, exactly the same shape. All right. Okay. Do you guys want me to show you how you can actually create your own patterns? Okay. So, let's find a pattern online and see. Okay. I will start with something that's fairly straightforward, something like this. Okay, so it's like a series of chevron logos. Okay, so it's easy to construct, easy to understand. I'm going to create a new file. By the way, before I do that, do you guys want to take a break? Yeah. How about we do a 15-minute break? And then we go into this file. Okay. So come back 35, 250, 15-minute break. Okay. All right.